titanium or tungsten. So you can see how different phase diagram relates to different material. Binary phase diagram for, again, different alloys. We're gonna study further. Another question is given here. Also, binary phase diagram for carbon in iron. I will go through it specifically, which is a very common example used in industry. And again, we're gonna have like a statements about steel. We're gonna go through a lecture slides on steel as well. We're gonna talk about different non-ferrous metal, for example, copper, nickel, chromium, aluminum. We're gonna just have a quick touch on it because we don't have time to go through everything. I'm just gonna just go through the most common used non-ferrous metal. And the last question again is related to a stress strain diagram. So as you can see in this 10 diagnostic equation, you will see the main focus is on, as is in the PPI book also agrees to it, is mainly focused on binary phase diagram and stress strain, which we're going to focus in this class. So I will open the PPI book. Some parts we can cover in the book, and some parts then we will switch to my lecture slides. Okay. Do you guys have any questions before we proceed? Everyone is good? Okay. So the topics we're going to look into, which is like chapter 34 in your book that you have, and I'm going to cover some topics from here, which I believe is like useful. Some topics I'm going to go switch to my lecture slide. We're going to talk about material selection, material science, electrical properties, thermal properties, mechanical properties, classification of material, engineering stress, engineering strain, which I'm mainly going to focus on my lecture slide, stress strain curve, point along the stress strain curve, allowable stress design, ultimate strength design, ductile and brittle material behavior, crack formation, crack propagation, which your book pretty fairly covered this. I'm going to use the PPI book. Fatigue is another phenomenon. We're just going to briefly talk about it. Since it's an extensive topic, we cannot go through all the details. Toughness, Charpy test for measuring toughness, ductile brittle transition, creep test, and hardness testing are the topics that I'm going to cover in my lecture slide in more depth. So materials basically follow in different categories. You have ceramic material, so you have ceramic material such as glass, graphite, diamond. Then you have a composite material, which is like a reinforced particle in a substrate, like a metal matrix composite, which actually my area of expertise is on metal matrix composite by 3D printing. Ferrous metals such as carbon alloy stainless steel and tool steel, which the basis is based on iron. Then you have non-ferrous metal such as aluminum, copper, nickel, titanium, and so on. Then you have plastic, thermoplastic, thermosets, and elastomers. So these are the different categories of material that are around us that are used in industry. Then we come down to material property. First, we're going to focus on electrical property. We're going to focus on capacitance. So when you have a capacitance, like that's a cross section A, and has a distance A, B in between. It has at the vacuum, it has a basically terms that you're gonna see is a emissivity in the vacuum. Then you have a correction factor K, which is multiplied by the emissive. There's a table here that also stabilizes different K value, which I'll show you earlier. But so basically, this is in the vacuum area, which is like a permittivity, and then the actual permittivity is a constant K multiplied by the permittivity in the vacuum. So Q is an electric load that is like a positive charge becomes negative. It's an electric load that has been like piled up based on the capacity multiplied by the voltage on each side. And C so is epsilon multiplied by the cross section A divided by D. So capacitance are used to store energy and release energy. There's an example here that says that two square plates have a cross section of 0.04 by 0.04 and are separated by a distance of 0.1 centimeter thick insulator. If a dielectric constant is 3.4, so K is 3.4. So as a result of that, the permittivity is equal to 3.4 multiplied by the permittivity in vacuum, which permittivity is vacuum, is 8.85 10⁻12 farads over meter. The unit is farads over meter. And so basically the way we can tackle this problem is that first we find the capacity. It's 3.4, which is the K value multiplied by the permittivity in vacuum multiplied by the cross section 0.04 power 2 divided by the distance between the two plates, which is like 0.1, and this gives the final answer. So you simply use the equation to find the capacitor epsilon multiplied by A divided by D. This also can be found in your equation book, but it's a simple equation just to memorize it without even having to go through the equation. Any question about capacitors before we proceed? Everyone is good? And the next part is resistivity. Resistance in material is an important factor to consider for electrical conductivity. So it's the resistivity rho multiplied by the length divided by A. So by the length, basically if the material has a higher length, the resistance of the material to electric current will increase, and we know that V, the voltage, is equal to R, the resistance, multiplied by R, the current. So as the length increases, the resistance increases. For the same voltage, you get a lower current passing through the material. I'm gonna just show you a table that you have also access to. For different material, different properties are given. For example, for metallic parts, you will get the Young's modulus, modulus of rigidity, Poisson ratio, coefficient of thermal expansion, and density. These are called physical properties of different material. You also get other properties such as atomic weight, density, melting point, specific heat, electric resistivity, which is the rho value, and also heat conductivity, which I'm going to elaborate on that when I go to the heat conductivity. So another example, like for example, a standard copper wire has a diameter of 1.66 millimeter. What is most nearly the resistance of 150 millimeter of wire at 0 centigrade? So as I talked to you, the resistance is equal to R rho multiplied by L divided by A, right? So in order to tackle this problem, the first step is to find resistivity. So you look to the table, which is also given to you during the test. You find the electric resistivity for copper. So I look for copper. And I look for electrical resistivity, which is 1.55 at 0 temperature. So I have the electric resistivity for copper. So it's like 1.55 for constant units multiplied by the 10 power minus 8, which is in the table, multiplied by the L, the length, divided by the cross section, pi over 4 d power 2. And I use like 1,000 power 2 to change the units from millimeter to meter. And that's the final answer that I get for resistance of the wire. Any question about this problem itself before I proceed? So that's another mechanical property, electrical property of material to consider. Semiconductors are another category of material that, just to let you know what semiconductors are, the electrical conductivity of the semiconductor is affected by temperature, light, magnetic field, and so on. Semiconductor imputes and increases this current based on an initial voltage that is put on the semiconductor. So as opposed to the normal material, a semiconductor can have the amplification of the current under a very small voltage. And it's very common to be used is transistors and other electric parts. So what are the common materials and transistors of semiconductors? The common materials are silicon and germanium and so on. So silica, Si, can be doped by other additives to increase its material properties, so it can amplify the current based on a small voltage. So the dopants are given in the table for you, just to give you an idea of what semiconductors are. The other material property is transduction principles. So different transducers can be used. Some of the examples of self-generating transducers are piezoelectric transducers, where piezoelectrics are at a low voltage, like zirconium is one example. It starts creating and amplifying something and making a vibration. Also, solenoid valve, using a solenoid under electricity, creates a magnetic field that the voltage fluctuates, the material can start moving back and forth, creating a transducer. And the next part is the thermal property, thermal capacity of materials. So this is the equation for it. MC delta T, amount of the heat flux that's been going into the material to change the temperature delta T. That is equal to M, the mass, multiplied by thermal capacity, multiplied by the change of temperature. And that's the equation that you will use if you see any equations of this sort about the thermal capacity. The other thermal property is thermal conductivity, which you can add. I have it in my lecture slide. I'm going to elaborate more. But thermal conductivity is if you have a material, this side is T1 and this side is T2.